we talked about how currents in a magnetic field experience a magnetic force. And we talked about how currents can create a magnetic field. So let's put those two things together and talk about how forces can appear between two parallel conductors that are carrying current. So I have two wires here. Wire 1 on the top going horizontally, wire 2 on the bottom. And wire 1 is going to have current I1. Wire 2 is going to have current I2. They don't have to be the same. This might be 2 amps and 4 amps, or a half amp and 100 amps, it doesn't matter. But they're independent currents. These wires are not attached to one another. They're just separated in space by some distance r. So this separation could be between two parallel. It could be very large, it could be meters or kilometers apart, or they could be very close, millimeters apart. So we're going to look at the force per unit length. So I have this drawn wrong. Let me correct that quickly. Magnetic force per unit length is equal to the following equation. And the length is just the length of the two wires. We're assuming both wires have the same length. The force per unit length is equal to mu naught, which is this permeability of free space constant, 4 pi times 10 to the minus 7 Teslas times meters over amperes, times the current going through wire 1, I1, times the current going through wire 2, I2, divided by 2 pi times the separation r between the two wires. So that gives the magnitude of the force per unit length. So if we know what the length is, we can put that in here and calculate what the total force is between the two wires. Again, assuming the wires have equal length. It's not the length of both wires together, it's just the length L here of each individual wire. Now, using this equation, we can calculate what the magnetic force is. However, we also need the direction. What direction are the forces of the wires? Well, actually, parallel currents, like I have drawn here, will attract one another. So what will happen is this wire will experience a force downward, F sub E. This wire will experience a force upward. And these two wires will want to come together. They'll experience a force of attraction. If I change the direction of the current of one of the wires, let's say I2, I change it and have the current going in this direction, then the forces will be repulsion. So the force here and here. They'll be wanting to divide or separate, push away from one another. Let's talk about that a little bit more than your book goes into that detail, because it really brings together a lot of what we've talked about so far this chapter. What's going on? Well, wire 1 has a current in it. So let's just look at wire 1 right now. Wire 1 has a current in it. That current generates a magnetic field around it. Wire 2 happens to be in that magnetic field, therefore experiences a magnetic force. Likewise, wire 2 generates a magnetic field around it from the current that's in the wire. Wire 1 happens to be in the magnetic field of wire 2. Now remember, wires and charges can't be pulled or pushed by their own magnetic field. The magnetic field that wire 1 generates can't push or pull on wire 1, right? You cannot be subject to your own forces. No matter how strong you are, you can't lift yourself up by your own bootstraps, right? You can walk up to someone else and pick them up, but you cannot pull yourself, no matter how hard you pull on your shoes, you won't lift yourself off the ground. So let's look at this in a little more detail. So wire 1 generates a magnetic field around it. Let's just pretend wire 1 is here by itself. What direction is that magnetic field? Well, wire 1 is going to your right. Thumb in the direction of the wire, grab the wire, so the magnetic field will make loops like this. So if the wire is going in this direction, the loops will be clockwise, but the wire is going in that direction. So up here, right, grab the wire, the magnetic field is coming out of the board. And down here by wire I2, the magnetic field is going into the board. Well, now we have a current I2 in that magnetic field. Let's use the right-hand rule again. Fingers in the direction of the current. Push the current onto the magnetic field. This shows you the direction of the force. The force on wire I2 will be downward. So this wire will be pushed down. Okay? Now let's erase the magnetic field from wire 1 and look at what happens to wire 2. Now wire 2 generates a magnetic field around it. Fingers in the direction of the wire, grab the wire. So the magnetic field here is into the board, above the wire 2. And below wire 2, it's coming out of the board. Okay, so where wire 1 is, the magnetic field is going into the board. So right-hand rule, fingers in the direction of the current, push the current onto the magnetic field. Your thumb is in the direction of the force. The force is upwards. The direction of the force will be upwards. So we just proved that anti-parallel currents, the forces will repel one another. And I could redo the experiment with parallel currents to show that the forces will attract, but I won't do that in this video. I'll leave that to an exercise. Try to convince yourselves of that. So this is the forces experienced between two parallel conductors that each have a current. Now there has to be a current in both, right? If I1 doesn't have a current, it doesn't generate a magnetic field. I2 isn't sitting in the magnetic field of I1 then, because I1 is 0. The magnetic field is 0. There is no repulsion or attraction. There is no magnetic force. If I2 is 0, there's no current in I2. It doesn't generate a magnetic field, so I1 doesn't feel a push or a pull. So you have to have currents flowing in both wires for this to happen. And in this simple equation, the wires have to be parallel. They have to be the same length L. They have to be separated constantly by distance R. If the wires, are wavy or come in, then the math becomes much more complex. You need calculus to solve it. So we're not going to get into that. We'll just look at this simplest case.